So the molarity of the solution is going to be the moles of solute divided by the liters of solution. We've seen that, right? We've dealt with that already in Chem 110. So for example, if I have 0.31 moles of vanillin, which is this compound here, and it's dissolved in enough diphenyl ether to give 1.5 liters of solution. So this time I'm not talking about an aqueous solution. This isn't water. This time our solvent isn't water, but it's diphenyl ether. Well, doesn't matter. This is moles of solute per liters of solution. There's my moles of solute, and there's my liters of solution. So the molarity is just going to be the 0.13 divided by the liters, 1.5 liters. So it's going to be 0.21. The unit here is the capital M, which is pronounced molarity. Okay, so we're going to say molarity, or this is the molar concentration. We're going to introduce another concentration here in just a minute that's called the mol concentration. So we have the molar concentration, and we're about to talk about the mol concentration. So the molar concentration is in moles per liter. So instead of writing out moles of vanillin per liters of diphenyl ether, I just say 0.21 moles of vanillin in diphenyl ether. Now on the quizzes, unless if I ask for you to give me the molarity, I'm going to tell you that I want it in units of moles per liter, and all you're going to enter in the Canvas is 0.21 to whatever sig figs are required, okay? Only enter units if there's a separate box that will literally say units, and don't ever enter the chemical. Now, unfortunately, that is not the way I would want you to do it. That's not the best way to do it. The reason I have to do it that way is if you enter this in some other way that might be correct, but not the way that I told Canvas to look at it, Canvas isn't smart enough to recognize that. So even though in real life you would report it like this, for example, on an exam, you'd report it like that. And again, do the homework problems. It's showing you the proper way to report your answers. It's showing you how to follow sig figs. So the solutions do all of it, okay? But anyway, in Canvas, though, you just report the number. Okay, now, we've also talked about another way to show concentration. And that was using mass percent. And so we've seen that the mass percent of a solution in this case, so if we're talking about the mass percent of a solute in a solution, it's just the mass of the solute divided by the total mass of the solution. So that's the solute plus solvent, right? The total mass of the solution times 100%. We already did that in Chem 110. So for example, let's calculate the mass percent of magnesium sulfate in a solution that contains 4.3 grams of magnesium sulfate in 148.8 grams of water. Well, again, it's just going to be the mass of the solute, in this case, the magnesium sulfate, divided by the mass of the solution, which will be the sum of the solute mass plus the solvent mass. And so there it is. So the mass percent would be 2.8% magnesium sulfate in solution or in water. Okay. Now, we generally deal with some very, very dilute solutions. So for example, if you had a 2.8% of an arsenic containing solution and you drank it, you would die very quickly. Okay. So there's allowable levels of, for example, of arsenic in your drinking water. It can never be zero. Okay, there's all in the water that you're drinking today, in that purified bottle of water, there is most likely some arsenic ions in it. But there is an acceptable level. There's a level that the body can handle, but it's not in this 100% range. Okay, so therefore I'm going to introduce two more types of concentration: parts per billion and parts per million. So in the case of parts per million, it's just a mass percentage, but this time instead of multiplying by 100, you're multiplying by 1,000,000. In the case of arsenic, the allowable limits are in parts per billion. So in that case, again, it's just the mass of the arsenic divided by the total mass of the solution times 1,000,000,000, 10 to the 9. Okay, so there's parts per million and parts per billion. They're just mass percentages for extremely dilute solutions. Okay, now we've already talked about mole fraction. And we said the mole fraction of a solute, in this case, is just going to be the moles of that particular solute, we'll call it component A of our mixture, our solution, divided by the total number of moles in the solution. So that's going to be the moles of solute A, and if there's solute B, C, and D, it'd be the sum of all those moles plus the moles of the solvent itself. So this is the total number of moles within the solution. And we've seen when we dealt with gases that we could get this mole fraction also by simply taking the partial pressure of the gas divided by the total pressure of the gas. So if we're dealing with gases, we could use that, right? The partial pressure of the gas divided by the total pressure. In this case, though, these are liquid solutions, so we're not using gases. So we have to go with just the moles of that given solute that we're interested in divided by the total moles in the solution, including the solvent. Okay? Okay. So for example, I want to know what is the mole fraction of fructose. Now, I would normally give you the mass of fructose, and then you just divide by the molar mass, right? To go back and forth between the mass and moles is always just the molar mass. If I give you the moles, you have the mass because you could always have a periodic table and you could always calculate the molar mass. So if I give you the number of moles, you already have the mass. If I give you the mass, you have the number of moles. It's just using the molar mass. So normally I would give you the mass and you'd have to convert this to the moles. But anyway, so we have 0.1 moles of fructose and we have 9 moles of water. Again, in this case, I'd probably give you a volume and a density. So you would go from the volume to the mass using the density, and then from the mass to the moles using the molar mass of water. Do your homework, okay? All those types of scenarios are there for you to solve, okay? Okay, so 0.1 mole of fructose and 9 moles of water. So the mole fraction then of fructose in the water is just going to be the moles of fructose divided by the total moles of the solution. So that's going to be the 0.1 mole of fructose plus the 9 moles of water. So there's the total number of moles in the solution. And again, if there was another solute, would add that into the total as well. So that tells us then that the mole fraction is 0.011. This is what we call a dimensionless value. It has no units. There's very few values in chemistry or science in general that have no units. And units are critical. No matter what the problem is, if you get the units wrong, I will take off at least 1 point. And if you don't give me units at all, I will take off at least 2 points, regardless of what the worth of the question is. So units are really, 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 really important. Okay, but in this case, mole fraction is dimensionless. It has no units. Okay, now mole percent, simply take that number and multiply it by 100%. So in this case, the mole percent of fructose is that there is 1.1% fructose in the mixture by mole, okay? Okay, now here comes a new one. This is molality. Molality is the moles of solute per kilogram of solvent. So this ain't the whole solution anymore, okay? This is the moles of solute, and this is the mass of just the solvent. So to go back and forth between molarity and molality, you need to know the densities of the solutions or the solvent, depending on which way you're going. Do your homework, okay? Okay, so for example, what's the molality of a solution that contains 0.17 moles of vanillin? Again, I would have given you that as a mass. Dissolved in 1.6 times 10 to the negative 3, or 1.6 kilograms, because it's got to be in kilograms. And again, if this is a liquid, I would have given it to you as a volume and a density, and you would have had to convert it to mass. So we're going to take the 0.17 moles of our solute and divide it by the mass in kilograms of our solvent, and that's going to give us the molality. So I would say this is that our solution is 0.11 mol of vanillin in diphenyl ether. Okay, so now this unit is a lowercase italic m. Don't confuse this for the variable of mass, which is also a lowercase italic m. Most units are not italic. All variables are italic. Okay, so a variable is a letter or a symbol that represents some value. Okay, and then the unit is just a way of expressing that number, like a dozen, right? So if I multiply, I have 24 eggs, right? I'm going to say that I have a dozen eggs. So that's what that unit is the dozen, okay? So again, the variable in units. And again, I will give you better examples of that as we go, because it's going to be important to be able to distinguish between the two. Okay, so again, this is just going to be called 0.11 mol of vanillin in diphenyl ether. Okay, so this is molality. Number 46 from chapter 13. It says a sample of caffeine with that molecular formula was dissolved in 50 grams of chloroform to give a 0.0578 mol solution. How many grams of caffeine were in the sample? Okay, so what am I going to do here? What do I know? I know that the mol concentration was 0.5, whoops, missed a 0.0578 mol. Let's see where we at. Michael, what does this lowercase m represent for this number? In other words, what does this all mean? 0.0578 what?
Molality.
Yeah, but what does that exactly mean?
Moles of solute per the kilograms of the solvent.
Okay, so I want you to be specific. Moles of what? What is our solute?
CHCl3.
That's the solvent. Dissolved in means that that's our solvent. So what is the solute?
Chloroform.
Chloroform is our solvent.
Okay, I'm reading it wrong. It's the caffeine then.
Yeah, it's caffeine, right? So C8H10N4O2. And then it is over what? Well, it's the kilograms of solvent. So what is the solvent? So what is the solvent? Okay, I'll let you go then. Make sure that you re-watch this, okay? Okay, Taylor, what is my solvent?
Is it the chloroform?
Yeah, now what would I specifically put down here though?
Would you have to convert 50 grams to kilograms?
Now be careful, molality. What is the definition of molality?
Mhm. molality is the mole of solute in over the kilograms of solvent.
Yeah, a kilogram of solvent, which our solvent is the, whoops, shit, is the chloroform. Okay? So that's what molality stands for. So instead of writing all of this, we just put a little m. That's why we do it. Okay? But when you're trying to do it in the calculation, you need to understand that that little m means all of this. So if we want to get the actual mass of the caffeine, so if we want the mass, and I'm just going to call it CAF, and the CAF, of course, this is CAF. Okay, so if we want the mass of the caffeine, well, I know that I can get mass from moles. So I need to know how many moles of caffeine there are. But that's the molarity, but I only have the 50 grams of chloroform. So to get the moles then, I'm going to have to multiply my molality, the moles of CAF, which is 1 kilogram of the solvent, by the mass of the solvent, which was 50 grams. I want it to cancel so the mass has to be in the numerator, so 50 grams of chloroform. But the kilograms and the grams aren't canceling, but I do know that there's 1,000 grams in 1 kilogram. So now the grams are canceling, and now I have kilograms canceling, and now I'm left with moles of caffeine. So everybody follow that so far? Okay, so now I am going to simply multiply this by the molar mass. So the moles of caffeine cancel, and now I have grams of caffeine. That's exactly what I was looking for. So plug that into your calculator, and you're going to get a value of 0.5615 grams of caffeine. Sig figs, we have 3 sig figs. The one we'll consider to be exact, and all the uncertainties in this. So there's 3. There's 1, 2, 3. This is exact. This has 5. Now, because all we're doing is multiplying and or dividing, it's the measured values with the fewest number of sig figs, which is 3. So that's how many our answer will have, 3. And so that then is 0.561 grams of caffeine are in a sample that contains 50 grams of chloroform with a molality of 0.0578 molality.
I have a question.
Yep.
So on an exam, if we just underlined in the answer what the significant digit is that?
I will take a point off.
Okay.
And here's why. Well, there's actually 2 reasons. Number one, outside this class, most people aren't going to know what the hell that means, right? You're like, why'd they underline that number? The second reason is I want to see that you're actually rounding these things correctly. Okay, so this is your final answer. This is not a final answer. I'm very glad you asked that. Okay, so this is your final answer. Okay, now I will tell you that any of you who've had me for Chem 110, I'm much less strict on sig figs in Chem 112 than I was in Chem 110. Okay.
Wait, I have a question real quick actually too. Where did the 194.19 come from?
That is, oh, I'm sorry. Okay, that's the molar mass. So you remember from Chem 110, what is the molar mass? It is simply the mass of all of the atoms within a compound, right? Mm-hmm. So if there's 8 carbon, each carbon is 12.0107 grams per mole. So it's going to be 8 times the 12. There are 10 hydrogens. Each hydrogen is 1.00794 grams per mole, so it'll be 10 times that plus that of the carbon. 4 nitrogens at 14.067, and the 2 oxygen at 15.994. Add all of that up, and you get 194.19 grams per mole.
Okay, and then what exactly did you do to get the final like 0.561? Like what did you multiply together?
I plugged into my calculator. 0.0578 times 50 divided by 1,000 times 194.19.
Okay, gotcha.
And if I would have actually done that correctly, sorry, and divided by 1,000 instead of 100, I would have gotten the 0.5612.
Okay.
Okay. Okay, everybody good? Okay, let's try the next one then. It says an antiseptic solution contains 0.788 molar hydrogen peroxide in water. What is the mole fraction of hydrogen peroxide? Okay, so again, remember what this means. If I have a 0.788 mole, which means I have moles of my solute, which is the hydrogen peroxide, and that is going to be per kilogram, then what is my solvent? What is my solvent?
The solvent would be the water.
Yeah, it's just water. It's in water, right? So that means I got 1 kilogram of water. Excuse me. What is the mole fraction? If I wanted to write an equation, what is the mole fraction of hydrogen peroxide? Kayla, what do you think? Remember, I just want an equation.
Yeah.
Would it be with the H2O go on top and the hydrogen peroxide on the bottom?
No. Does anybody want to help her? You can leave the bus just roll right over her?
It's the moles of like one certain compound. So in this case, it's going to be the hydrogen peroxide on top.
Yes, because I'm looking for the mole fraction.
The total, what?
Yes, yes. I'm sorry. Go ahead. By the total what?
Oh, by the total moles in the whole like solution, like the.
So you're saying it's moles of the hydrogen peroxide.
Yeah.
And what is the total then? Be very specific.
Moles of hydrogen peroxide plus moles of H2 of the water.
Yeah, of the solvent, right?
Okay.
So there it is. There's your mole fraction. Okay. Okay, how many moles of H2O2 do I have? Katrin, what do you think? How many moles of H2O2? You got to hit your space bar.
Sorry, I thought I did. 0.788.
Okay. So, well, you're on a roll now. So how many moles of water?
That'd be like 1 kilogram of water converted into moles.
Okay, exactly. And how am I going to do that?
Gonna
1 kilogram of water.
and then multiply that to get it into grams.
Okay,
Or
so
convert it into
so multiply it by what or divide it by what?
multiply by like 1,000 over 1.
Exactly right, because in 1 kilogram there is 1,000. Now I'm going to tell you, and I'm going to preach constantly, please make sure that you're using units in your calculations and chemicals where appropriate. It is going to save you a bunch of stupid little math errors where you divide this by 1,000. Okay, if you would have wrote it down, you would have realized that you got it flipped. And would have saved you 2 points. And trust me, those 2 points add up real quick on exams. So please make sure you use units in your calculations. Okay, I'm sorry, Kaylee. Okay, so the kilograms cancel. I'm not Kaylee, Katrin. So now what? Now what would I do?
Then you would divide again by the molar mass.
Okay, so the molar mass again, we have hydrogen at 1.00794 grams per mole times 2, since there's 2 hydrogen, plus the 15.994 grams per mole gives us 18.015 grams of H2O for every 1 mole of H2O. Again, using the units, I could see that, yes, I had to divide because the grams of H2O cancel, and now I have moles of H2O. And plug that into your calculator, and you would get a number, I'm pretty sure, of 55.509 moles of H2O. Now, in this case, we are considering the 1 to be exact. This would be exact. So just the molar mass that we decided to use determined how many sig figs. In this case, we used 5. So that's way out to there, okay? So that's now the moles of water. And by the way, if I don't have this paper where you can see it, please speak up and tell me, because a lot of times I'll start writing down here and not realize that you can't see any of it. So just say, hey, move it up, okay? Okay, now we have mixed operations for following sig figs. Now I have addition mixed with multiplication division. Now with addition, we're looking for the value with the fewest number of significant decimal places. So when I plug this into my calculator, okay, I'm going to get an intermediate value of 56.297 moles. Okay, so 56.297. Well, this is 1, 2, 3 passed. And this is 1, 2, 3 passed. So this is going to be 1, 2, 3 passed. Then finally, we're going to take the 0.78 and divide it by the 56. That's going to give us a value of 0.013997. No units now, right? Because the moles cancel the moles, so there's no units. And this now is 3 sig figs. This is 5, so this is 3. And so your final answer would have been 0.0140. Okay, don't forget those zeros that are significant. And that would be your answer. So this 0.788 molar hydrogen peroxide in water is the same thing as having a mole fraction of H2O2 of 0.0140. Any questions with that? And again, if you miss anything, you could always go back to the video. The video of yesterday's is posted on Canvas. I don't know if anybody, well, nobody's looked at it yet. I've seen that. But if you do need it, it's there, okay? Okay, so let's try another one. This is number 28. It says citric acid with the formula C3H6H5O7 naturally occurs in a variety of fruits and vegetables. Lemons and limes contain the highest concentration of 5 to 8% citric acid by mass. What I want you to do is determine the molar concentration. Well, molar is that capital M, right? The molar concentration of an aqueous solution, so we know we got water, so that is 0.305 mole citric acid. Well, we've already established that that means that there's that many moles of citric acid. Now, I'm going to call this thing CIT, just so I don't have to keep rewriting this entire formula, okay? So moles of CIT, which is our citric acid, and our solvent is water, right? So it would be 1 kilogram of water. So this is the mole concentration of the citric acid in water. Okay, now we want to go to the molar concentration. So the molar concentration is going to be the moles of citric acid over liters of solution. So what are the moles of citric acid going to be? Eugenie, what do you think? What are the moles of citric acid going to be? You got to hit your space bar.
5 to 8%.
No, moles. That's a percent. That's actually a mass percent. I want to know how many moles of citric acid there are.
So then would you take the mass?
What does
Divide
this mean again?
Oh, that's molar.
Well, right? So do you know how many moles of citric acid there are then? Here it is written out.
Oh, citric acid is the solvent. So the citric acid is the solvent, right?
That's our solute. Water is our solvent.
Okay, so
What is aqueous?
so would the 0.305 be the mole?
Yeah, right. It's just 0.0305 moles of citric acid. Okay. Okay, Keenan. What about the liters of solution?
Yeah, I was kind of thinking about that. I'm not really sure how to go about that.
Yeah, Leah.
Would you use the density to convert the 1 kilogram to grams, and then from grams to milliliters?
Okay, so the density is equal to the mass divided by the volume, right?
Mm-hmm.
And we want a volume. This is a volume. So if I rearrange this equation, the volume then is equal to the mass divided by the density, which is the same thing as the mass times the inverse of the density.
Yes.
Now, what is the mass of the solution? Remember, this is solution. What is the mass of the solution?
I mean,
What
it's
is
going to
this?
be the volume of both the citric acid and the water.
So the mass of both of them.
Mm-hmm.
We know the mass of the water?
Wait. Yeah, technically we could solve for it.
Okay, so what's the mass?
Kilograms to, just multiply. Well, if it says there's only 1 kilogram of water, then shouldn't we just convert it to grams? And
Yeah,
then
there's 1 kilogram of water. So we have 1 kilogram of water, and I'm going to convert it to grams because our density was given to us in grams per milliliter. So I'm going to convert that, and I'm going to ignore the chemical here because we're looking for the total mass. So there's the 1 kilogram of water. So right, this is the water, H2O right here. So that's the 1 kilogram of water. And in 1 kilogram, there's 1,000 grams. So now we have grams. But what else is in there?
the citric acid.
The citric acid. So how am I going to find the mass of the citric acid?
Well, we have the moles, so just multiply by the molar mass.
Yeah, exactly right. Again, I stress, if we have moles, we know the mass because we always have a periodic table. We always know the molar mass. We could always calculate the molar mass. And if you have the moles, you have the mass. If you have the mass, you have the moles, no matter what. As long as you know the chemical formula, you always have it. So we know that we had the 0.305 moles of citric acid, okay? And we're going to determine the molar mass from the periodic table. Again, here's our citric acid. There's 3 hydrogen. There's actually 8 hydrogen. It's written like this because this is an acid and it's a triprotic acid. 3 of these hydrogens are actually acidic. So there's 8 hydrogen, so 8 times the 1.00794, 6 carbons times the 12.01, plus the 7 oxygen at times 15.994, and that gives you a molar mass then of citric acid of 192.125 grams of citric acid per mole of citric acid. So the moles cancel. And now I have grams plus grams, right? That has to be that way. And so that mass then, that total mass would be equal to 1,058.598 grams. This is exact. So this has, there's actually a mixed operation here that you would have to take into account. And basically then that is going to put the, this is going to end up being 58.598, and that's 3 sig figs, that's 6, so that'd be 3, so this is going to be 1 passed. And then finally, we can get the volume. So the volume then is going to be the mass that we just calculated. Okay. We're going to multiply it by the inverse of the density, which means we just flip it. The grams cancel. But remember, for molarity, it's very specifically liters of solution. So I need to convert my milliliters to liters, and there's 1,000 milliliters in a liter. So my milliliters cancel, and now I have the units that I want, the liters. Plug that in, and that's going to be 1.0198 liters. So this has 5 sig figs, this has 4, this is exact, so this will be 4. So now I have my moles already, now I have my liters. Excuse me, plug that into your calculator, and you get 0.29906 moles per liter. 3 sig figs, 4 sig figs, so this is only 3. So your final answer would be 0.299 molar citric acid. And there would be your final answer. Okay. Any questions about any of that good stuff?
Can I just clarify something, I think?
Yep.
So your density is the water plus the citric acid.
That's the
density of the whole solution.
That's the density of the solution. Therefore, you need
Okay.
the mass of the whole solution.
Yeah.
Now, if you were going the other way, if you were going to molarity to molality, then you need the density of the solvent, just
Okay.
the density of the solvent. Again, do the homework problems. I have homework that goes both ways.
Okay.
So from going from molality to molarity, you need the density of the solution. Going from molarity to molality, you need the density of the solvent.
Okay. All right. Thank you.
Any other questions? Okay, let us try another. So this says a solution in which 2.24 grams of naphthalene, which is CaH10, and I'm going to call this NAP. Okay, so naphthalene in 40.9 grams of benzene, which has the formula C6H6. I'll just write that out, it's short enough. Has a vapor pressure of 83.2 torr. So now that's the vapor pressure of the solution, right? Is 83.2 torr. Again, a lot of times it is good to write down the values that you recognize using the variables that they belong to. That's going to make using the correct equation a lot easier. Okay? So again, this is why I stress you need to know what your variables are, because those are in your equations. If you know the variables that are represented by what's being said in the sentence, you're going to be able to understand what equations you need to use. Okay? Okay, so again, we have the mass of the naphthalene. So we have the mass of the naphthalene equal to 2.24 grams. And it wants us to determine the vapor pressure of pure benzene at the same temperature. So pure benzene now at the same temperature. So what are we looking for? Well, that would be this. Well, let's call this C6H6. So this is what we're looking for. Just a real quick side note. Does anybody know what naphthalene is? Most of you have probably never bought it, but I guarantee that your grandparents did. You ever hear of mothballs? Okay. So mothballs are these little white balls, and they have I can't describe the smell. It is very unique. If you've ever smelled them, you know what I'm talking about. I don't know how you would describe it. They're potent, they're very strong, and they basically keep moths away. I don't know if they kill them or the moths just can't stand the smell of them because they smell so bad. But again, they used to throw them. It used to be that our clothes were much less synthetic, and they were like pure cotton, pure wool. And in particular, moths love wool. That's like candy to them. And so if you stored your wool blankets and shirts and jackets, by the time you'd use them the next season, they'd be full of holes because the moths would come in and, well, it's actually the larvae of the moth would come in and eat them. And the mothballs prevented that. But anyway, so just reminiscing about being old. Okay, so now let's come back to this. So I want to determine the vapor pressure of pure benzene. So what am I going to do? How am I going to solve this? What equation am I going to use? There's other important wording that I did not read yet either.
Rowlett's, I don't know how you pronounce it.
Raoul's
law.
Okay. 4, there's 2 Raoul's law.
Oh. The wait, hold on. Yeah, it's a solid. So
Yeah, it's a solid and it's non-volatile. It tells you it's non-volatile.
So that, yeah.
Okay, so what is that equation then?
Well, the partial pressure of the solution is equal to the pure version of C6H6 times.
So that is the solvent, right?
Yeah, the solvent.
So it's a solution and then the solvent. And then go ahead.
And then times basically the mole fraction of the solvent.
Okay, now I'll make this a little bit more specific, right? So our solution is the naphthalene in benzene. So I'll just keep calling that the solution. The solvent is the benzene, right? So this was dissolved in this. So this is our solvent, and then that would be the mole fraction of the solvent. And I am looking for this, right? So I would simply rearrange this equation then. The vapor pressure of the pure solvent is then just going to be the vapor pressure of the solution, divide both sides by the mole fraction of the solvent, benzene. Okay, so do I know the partial pressure of the solution?
Yes.
Yeah, it was given to us, right? So that's just 83.2 torr. How am I going to get the mole fraction of the benzene? Well, we've seen that already, right? So that's going to be the mole fraction of the benzene. Are going to be the moles of benzene over the total number of moles. So the moles of benzene plus the moles of our solute, which is the naphthalene, which I'm just going to write as nap. So now I got to get the moles of each. So the moles of benzene, well, they already gave us the mass of benzene, right? Or I'm sorry, they gave us the mass of benzene. So that was 40.9 grams of benzene. To get the moles, I'm just going to divide by the molar mass. So again, there's 6 carbon at 12.0107 grams per mole, plus the 6 times the 1.00794 grams per mole for the hydrogen. So that's going to give us then a molarity of 78.111 grams of benzene per mole of benzene. Which is going to give us then a total of 0.52326 moles of benzene. So this is what, 3 sig figs, so this would be 3. And then the moles of naphthalene, we're going to do the same thing. They gave us the mass of naphthalene is 2.24 grams. So that'll be the 2.24 grams of naphthalene. Again, naphthalene had the formula of C8H8, so that's 12.0107 grams per mole times 10 plus 8 times the 1.00794 grams for the hydrogen, giving you a molar mass of 128.17 grams of naphthalene for every 1 mole of naphthalene. The grams of naphthalene cancel, and that would give you then 0.017477 moles of naphthalene, 3 sig figs. So now we can plug that all into here. So the moles of benzene we just determined to be 0.5233361 moles. I'm going to ignore these now because we know that this is going to end up being unitless. So again, now it's the moles again of our solvent plus the moles of our solute. Mixed operations, so this plus this is actually going to be equal to 0.54109 moles. So this is 1, 2, 3 passed. This is 1, 2, 3, 4 passed. So this can only be 3 passed. Now we're going to plug this into our calculator. So the moles are going to cancel. And that's going to give me a mole fraction of 0.9677. We have 3 sig figs. We have 3 sig figs. So this will be 3 sig figs. And then now we just put in 0.9677, and it's unitless, right? So remember, the mole fraction is dimensionless. The units cancel. Plug that into your calculator. That's going to give you 85.976 torr. We have 3 sig figs, 3 sig figs. So that's going to be 86.0 torr. So that is the vapor pressure of pure benzene at 23 degrees Celsius. Okay. Any questions about that guy?